Assalamualaikum and very good evening to our lecturer Dr. Shafiq Azwan. We from Group 3 will present on the statistical process control approach in monitoring a latex glove production plant. In this presentation, we will explain on the product quality, control limit calculation, control chart discussion, QSUM chart calculation, cause and effect diagram, process capability, and lastly the sampling plan. Product quality can be determined by both physical and chemical properties of glove. The first one is the thickness of glove, which usually affected due to improper coagulant dipping process involving calcium nitrate. The user will lose the mobility of their hand if the glove is too thick. However, the glove will break easily and probably causes direct physical contact of the user with the chemical used if the glove is too thin. Hence, it is important to maintain an optimum thickness of glove. The second one is a total aqueous extractable protein, which usually affected due to improper leaching process. A longer leaching process can wash out the residual latex protein more effectively. However, it might cause some allergy to the user if the TAEP is too high. The concentration might drop if the leaching solution has been used for some time, which causes the TAEP to be out of control. Hence, to maintain the TAEP at required level, it is important to regularly check and add up the leaching solution. Next, I'll pass the floor to Henry.
Thank you, Hani. I'm Henry, and I'm going to explain on the control chart and also the QSUM chart. So first, for the control chart, we'll use the first 25 data to construct our control limit, and we'll check if there's any data point out of control. If yes, then we will find the assignable cost and revise the control limit. But if no, then we will use the constructed control chart to monitor our subsequent data, and we will make comments on the data behavior in our control chart. So for the control chart setup, we going to have assumption on assignable costs are being found for revised control limit, and then we will calculate the X bar and S from each data from M equals to 1 to 25, and we will require the data of N, which is sample number 13, and C4, A3, B4 and B3 are actually the constant that can be obtained from the appendix table, and the process mean and S bar can be obtained through the first 35 data points. And after this, we will calculate the upper control limit and lower control limit for X bar chart and S chart using this formula over here. For the revised version of the control limit, the subgroup number, process mean and S bar will be changed, and this will be changed according to the number of data that has been eliminated. So for example, initially we have 25 data points, then we found that there are 3 data points out of the control, then we will use 25 minus 3, so we will left with 22 subgroup number, and process mean, S bar, UCL and LCL will be changed as well accordingly. So for the control limit that we have constructed for thickness, you can see that the X bar chart and S chart, they have well distributed data points within the control limit, so this can be used for further monitoring purpose in phase 2. And then for TAEP control limit, we can see that the initial control limit, there are 3 data points out of control in X bar chart and 1 data point out of control in S chart, which is 5, 6, 16 for X bar chart, and 16 for S chart. So we will then use this we will then eliminate these 3 data points out of the calculation for both X bar chart and also S chart, and we'll assume that the assignable cost has been found. And after this, the revised control limit will check whether there's any new data points out of control. If there is no new data points out of control, then we can proceed with monitoring purpose in phase 2. So in phase 2, we will discuss the control chart based on synthesizing rule and also process knowledge. As we can see from X bar chart here of thickness, there are 2 data points, 126 and 130 out of the control limit of 2 sigma, and this might be due to the change of inspection skills of the operator that measures the glove thickness. After this, we look at S chart where 0.25 to 26 there's a sharp decrease in the standard deviation value, and from 26 to 130 we can see that the trend remains consistent, and this might be due to the process equipment error or sampling problem that have to be resolved. After this, we can see that from 115 to 116 the variability returns back to normal, but it is still not that stable because there's 8 consecutive data points on one side of the center line. So these issues on both sides have to be solved by rechecking the process equipment or revise the sampling plan. After this, for TAEP control chart, we can see that there are 4 data points out of the upper control limit, and this might be due to operator fatigue because this happened at 1 AM to 4 AM, and up to the knowledge that I know is that during the night time there will be more problem in the plant than the daytime because operator might sleep at the night time, and this have to be solved by having a stricter rules in the plant. And after this, we can see that from 0.124 to 130 there's an out of control signal over here, and this might be due to the leaching solution that is not being replaced with a new one, because as we know that the leaching solution initially is used to extract protein from the glove, but after a long time that have been used, the concentration of that will be reduced and as well as the effectiveness, so it has to be replaced with a new one. Also, after this, look at S chart. From 0.25 to 26 we can see that the value decreases sharply, and from 26 to 130 the standard deviation have been shifted to a lower side, which the process is showing lack of natural variability, and the shifting of this standard deviation can be proved by using the hypothesis rule, and if necessary we have to revise the control limit afterwards. So for the Q-sum chart, we'll start off with the calculation part where we obtain all the required data before calculating CI plus and CI minus, and then our assumption is that the process is in control and the observations are normally distributed. So we will obtain the X double bar and S bar from our table, and for the S bar, for the thickness we use M equals to 25, and for TAEP is M equals to 22 because we have already revised the control chart. And for C4 we can obtain it through the appendix table where N equals to 13, and the estimated standard deviation can be calculated using the equation here where we use S bar over C4, and the H and K are the given parameter in the project question, and the capital H and capital K can be calculated through the equation over here, and the mu naught is equals to our process mean, which is X double bar, and mu naught plus K and mu naught minus K are calculated prior to calculating the CI plus and CI minus, and at the end we use CI plus, CI minus and our H decision interval to plot our control chart. So this is our Q-sum thickness Q-sum chart, and over here we can see that there's no significant variations when we use the given parameter, and we further reduce down the K value to 0.25 to increase the sensitivity, but the variations is not that significant either. So at the end we reduce it down the K value to 0.1 and we see slightly better variations, and then we compare this one to our X bar chart. So over here in this case we can see that the K values is reduced to 0.1. As seen from a Q-sum chart, the variations of the data are more obvious as the uptrend of CI plus is showing something over here and is giving some hints that the process might be out of control soon if the data points are still in this area, if the X bar is still in this area. So it is advisable for the operator or the supervisor to take note on the production site. And moving on to the TAEP Q-sum chart, we can see that at first we use the given parameter, but then there's no significant variations over here. There's only one shift is detected, so we further reduce it down to 0.25 and we can detect 2 shift over here, and then we compare this table this chart to the X bar chart, and we can see that this variations is caused by this X bar chart shift over here, and the other one is caused by the shift over here, as we can see. So we can see that the point that the shift happened is from 66 to 67, and which is the same as here, and the other point is happened at 127 to 128. So here the shift is detected at first as 67, and over here the other one is detected as 0.128, where it is not detected previously at k equals to 0.75. So for monitoring of the small shift k equals to 0.25, the settings will be used is h equals to 3 and k equals to 0.25. And this something to discuss over here is that the CI plus shifting upwards normally means that the wear and tear of equipment is happening, and preventive maintenance should be carried out regularly. And that's all from me. I would like to pass the floor to Shavina. Thank you.
Thank you, Henry. I'm Sharvina here, who will be presenting on the process capability. The assumption for the process capability is the process in statistical control and the observation are normally distributed. As for the thickness of the glove, the CP value is 2.71, which is more than two-sided specification CP, which is 1.33. So the process is within specification limit and has low rejection rate. This shows the tolerance for the thickness is high. Next is the CPK value, which is also 2.7.71, as the process is centered at the midpoint of the specification. The CPM value is 2.71, which is also equals to CPK value that indicates the process is centered and on target at CP. Moving on to the total aqueous extractable protein concentration after revised. The CP value is 1.003, which is less than two-sided specification of CP 1.33. So the process is not within specification limit and has high rejection rate. This process has to be modified to obtain higher PCR and to compete with other manufacturers. The CPK value for TAEP is 0.7635, which is less than CP. This shows the process is half-center in the normal distribution curve, and the CPM value is 0.814, which is not suitable to measure for the centering as the sigma is not approaching 0 and the process average moves off the target. That's all from me. Thank you. I'll pass the floor to Liana.
Thank you, Henry. My name is Liana and I'll be explaining about the cause and effect diagram. The first problem is easily torn glove. The causes of this problem are, firstly, the machines involved in the process are late for maintenance, hence it cannot perform at the expected rate. The glove formers used in the process are not clean as there is dirt or debris. The heating system is not powerful enough for complete drying. Secondly, the measurements taken during the physical dimension test are inaccurate or the equipment for measurement is set at an inappropriate setting. Thirdly, there is poor latex pickup on the former surface as well as uneven coagulant distribution in the coagulant tank. Fourthly, the temperature and time specification used in the coagulating and dipping process is not suitable to achieve the test objective. Additionally, the environment is not clean, hence there is dirt trapped in the glove formers and the process line in the coagulant tank is too short. Lastly, the operator does not follow the SOP properly, or the operator is inexperienced, or the operator is untrained. The next problem discussed is the surface of the glove is too sensitive as the residual chemicals and proteins on the surface of the glove are not completely removed. The causes of this problem are divided into multiple branches. Firstly, the machines involved in the process are due for maintenance, hence it cannot perform at expected rate. The pumping system for the water exchange rate cannot achieve the needed heat. The heating system that heats up the water is losing too much heat to the environment. Secondly, during the protein test, the sample taken might be inaccurate or the equipment used for testing is set at inappropriate setting. Thirdly, the material in the leaching process such as water is contaminated or the water is too cold to make the proteins dissolve in the solution. Next, The specification used, such as the temperature and the time, are not optimum for the protein removal, or the technique for leaching process is improper. Additionally, glove is not properly dried by the dryer, or the process line is too short to wash out the proteins more effectively. Lastly, the operator does not follow the SOP properly, or the operator is inexperienced, or the operator is untrained.
Thank you very much, Liana. I'm Kamran, and I'll be discussing the sampling plan for our group. So to start off sampling plan, there are three types, namely single, double, and multiple sampling types. So in single sampling plan, the decision whether to accept or reject the lot is based on the sample taken once, whereas in double sampling, a second sample is required before the lot can be sentenced. And finally, multiple sampling is basically an extension of that, where more samples are taken into account in sentencing the lot. So in all of these three sampling types, there are three inspection levels, namely normal, reduced, and tightened. The way we switch between them is highlighted in this figure. So we start off with normal inspection. If 2 out of 5 consecutive lots are rejected, then we intensify to tighten inspection. If it gets further worse, as in like if 10 consecutive lots remain on tightened inspection, then we discontinue the inspection, and the decision on the supplier level has to be taken on improving the lot quality, the supply quality. On the other hand, if 5 consecutive lots are accepted, then we can relax back to normal inspection. From normal to reduced, these three conditions have to be met together, and from reduced to normal, any one of these conditions need to be met. Moving on, as we discuss the sampling plan for our project, a general inspection level 2, which is considered normal, it was taken with an AQL set at 4 and a lot size at 70,000 for a single sampling taken from tables 2A, B, and C in the Military Standard 105E. We can see the conditions for normal, tightened, and reduced inspections. Here we see the sample size, the acceptance, and the rejection criteria. Here we see the double sampling plan for the same conditions taken from tables 3A, B, and C. You can see there's the criteria for first and second sample for normal, tightened, and reduced inspection. Further moving on, for multiple sampling with a normal inspection taken from table 4A, we see the criteria for first up to 7 sample. The same for multiple sampling and a tightened inspection taken from table 4B. You can see criteria of first to 7th. And finally, for multiple sampling at a reduced inspection taken from table 4C, the conditions are listed here. With that, I'd like to conclude our sampling plan. Thank you very much for listening.